Have you ever found yourself struggling with linear algebra? We learn about different concepts in linear algebra. We learn about the different ways to calculate eigenvalues, eigenvectors, decompositions, and all that good stuff. And yet, we do not know how the different ideas in linear algebra come together. When we are facing problems that combine different ideas together, we don't even know where to start. Today, we're going to summarize linear algebra in a nutshell. The name itself is an amazing starting point. This is called linear algebra. What are we talking about when we say linear and algebra? Linear conveys the idea of lines, or roughly speaking, flat objects. And algebra refers to all of the different calculations and transformations that you can do to these lines and flat objects. What this means is that the heart of linear algebra can be broken down into two different ideas: vector spaces and linear transformations. But what do we mean by vector spaces and linear transformations? Well, what do we mean by a vector? Roughly speaking, we need a vector space to obey some vector space rules or axioms. And there are a bunch of different axioms. But roughly speaking, we want vector spaces to behave nicely under two different operations: addition and stretching. There are 8 rules that help us ascertain that these operations behave sufficiently nicely for our calculations. And when we start out with linear algebra, we want to work with something that's a little bit more concrete and a little less abstract. So we like to work with 2-dimensional vectors, 3-dimensional vectors, and in fact, we can go all the way to n-dimensional vectors. So when we talk about n-dimensional vectors, we can ascertain that under our definitions of addition and scalar multiplication, we will see that the n-dimensional vectors satisfy our vector space axioms. And now we can talk about objects called vector spaces and perhaps smaller parts of those vector spaces. In math, we like to describe smaller with the prefix sub, so we want to talk about this idea of subspaces. What exactly is a subspace in our context? Well, it's a smaller space that still has the nice properties of addition and scalar multiplication. The key insight here: to create such a space, we'll start with a bunch of vectors, say S, and consider all the different possible ways we can combine them so that addition remains nice and scalar multiplication remains nice. We're taking, technically speaking, all of the linear combinations of the vectors in S, and we're putting them all into a single set. All the different linear combinations, when you combine addition, scalar multiplication, and all that good stuff, can be summarized using the notation, the span of S. And at the same time, we want this span of S to be succinct enough for us to make calculations. What if the set S contains a lot of irrelevant information? Vectors that depend on one another. Can we talk about vectors that are fundamentally different from one another? This is where we will define the idea of a set being linearly independent. And a set being linearly independent basically means that if you can find a linear combination of these vectors that equals to 0, there's only one actual conclusion: that there's 0 contribution from any one of them. If we do have the span of a set, and this set is really containing all of the essential information about that particular subspace, in other words, this set is linearly independent, we call this set a basis of the subspace. And in a weird way, the basis really fundamentally describes a subspace. And we can use bases to solve all sorts of problems, as we're going to take a look later on. Suppose now we have a subspace V whose basis is S. Since S is linearly independent, being a basis, it sort of contains the minimal amount of information to describe the subspace. We call the number of vectors in this basis the dimension of the subspace. In fact, a very common basis that we tend to use is the x, y, z coordinate system, which in n dimensions is what we call the standard basis of the n-dimensional space, and we tend to represent this basis using the notation E subscript I. However, subspaces can all have different bases. We can choose different vectors that are linearly independent that represents the subspace. And for each of these bases, we will get a unique collection of coordinates that describes vectors in the subspace. This is called the coordinate vector with respect to the basis. But how do we convert coordinate vectors from one basis to another? In other words, if we are given coordinate vectors with respect to a basis S, and we have the coordinate vectors of the same vector, but with respect to a different basis T, how do we convert from one collection of coordinate vectors to another? We will use transition matrices to convert from one basis to another. And once we can convert from one basis to another, we can, in principle, fully understand everything about that particular vector space given the amount of information that we currently have. However, linear algebra isn't just about vector spaces. It's also about how you can transform these spaces from one kind of space to another. How do we describe such transformations? Since we are considering transformations of vector spaces, these are all linear, and therefore these are linear transformations. How do we describe linear transformations? When it comes to n-dimensional space, we have a very handy tool to help us do just that. This tool is known as a matrix. Just like the vector space rules, there are linear transformations rules as well. More precisely, when we talk about the vector space rules, we want these properties. If we have U and V in a subspace, then their sum should remain in the subspace. And if you have a vector in the subspace V that's stretched out by some scalar, the stretched out vector should also remain in the subspace. And hence we also have some similar linear transformation rules. Given a linear transformation T, when we plug in the sum, the transformation on the sum should be the sum of the transformations. And the transformation of the stretch should be the stretch of the transformation. It turns out that just as how n-dimensional vectors satisfy the vector space rules, matrices very cleanly satisfy the linear transformation rules as well. In fact, every linear transformation can be represented by a matrix and vice versa. We'll call this matrix A. When we talk about these transformations, what are some of its implications? We can consider all of the outputs. This is known as the range of T. And what's amazing is that when you collect all of these outputs, the range of T is a subspace, first and foremost. And secondly, it is the same as the space which you obtain by taking the span of the columns of A. In that regard, the range of T is precisely the column space of A. And both are subspaces, both satisfy the fundamental ideas of vector spaces. Similarly, we can consider all of the different inputs such that T of that input is 0. It's entirely possible. It turns out that the collection of inputs V such that TV equals to 0 also forms a subspace. This is called the kernel of T, and this is the same space that you will obtain if you find all of the different vectors V such that AV equals to 0. This is called the null space of A, and this equals to the kernel of T, and these are both subspaces as well. And they follow the basic rules of vector spaces. When you consider these spaces as vector spaces, they all have their bases, and thus they have their dimensions. We call the dimension of the column space of A the rank of A, and we call the dimension of the null space of A as the nullity of A. These two quantities are fundamentally connected via the rank-nullity theorem, which tells us that the rank of A plus the nullity of A is precisely the number of columns in A. But given a matrix A, we could try to multiply itself multiple times. This gives us a transformation on a transformation on a transformation n times. However, the power of a matrix is really difficult to compute. If we remember how to compute matrix multiplication, it involves a really long computational process. How can we do this in a much shorter manner? It turns out that a special kind of matrix called a diagonal matrix is really easy to compute. Just raise each entry to the nth power and we are good to go. Could we diagonalize A? In the sense that, could we write A in terms of a diagonal matrix? And that allows raising A to the nth power to be a relatively easy task. If such a process is possible, we will say that A is diagonalizable. And more precisely, we can write A in terms of D via what we call an invertible matrix. However, that raises a very important question for our consideration. When is A diagonalizable? It would be great if A is diagonalizable, but how do we know if it's possible? It will be possible when its eigenvalues and eigenvectors satisfy some conditions. What exactly do we mean by eigenvalues and eigenvectors? Eigenvalues refer to scalars and eigenvectors refer to vectors that satisfies a really clean multiplication property. If the vector v upon matrix multiplication gives the same result as the vector after scalar multiplication, we call the vector an eigenvector and the scalar the eigenvalue that it's associated to. And the matrix A is diagonalizable precisely when its eigenvectors forms a basis for Rn. So it's a really interesting property, except how do we even obtain eigenvectors and eigenvalues? We're going to have to solve an equation. We need to find the vectors and the scalars. We need to find the vectors and the scalars that satisfy the equation AV equals to lambda V. This requires us to solve a system of equations. The way we can solve these equations is through the method called Gaussian elimination. If you want to reduce it even further, you can use Gauss-Jordan elimination. And this question about solving systems of equations is a really interesting one because there is a system that will always have solutions. It will be the system where you have a matrix multiplied by a vector equals to 0. Because this system always have v equals 0 as a solution. We call this the trivial solution. And sometimes this is the only solution. If this is the only solution, it turns out that M is what we call invertible. In other words, you can divide out by a matrix. And there are many ways to establish invertibility. Some prominent examples include if the determinant of the matrix is non-zero. Another situation is when 0 is not an eigenvalue of the matrix. There are a few other ways to determine invertibility based on what we already understand. We have that the matrix is invertible precisely when its null space is just the 0 vector. What that means is that the column space of M must be everything. And this just scratches the surface on how we can tell a matrix is invertible. What's even more fascinating is that the moment you know a matrix is invertible, you get all of these properties for free. Now let's back up a bit and ask about perpendicularity. In 2 dimensions, the idea of perpendicularity is a relatively easy idea to grapple with. Is there a consistent way to define perpendicularity in higher dimensions? Perhaps even infinitely many dimensions? While the discussion on infinitely many dimensions will be reserved for future studies on functional analysis, for the finite dimensional case, we can describe it with relative ease. In this context, we will rename perpendicularity with orthogonality, and that is obtained precisely when the dot product equals to 0. This helps us talk about the idea of perpendicular vectors or orthogonal vectors. And that agrees a lot with our idea of the x, y, and z axes being perpendicular to one another. Now, given any subspace, we have a basis, but can we make that basis orthogonal? Can we convert that basis so that not only are the vectors linearly independent, in other words, they are the bare essentials of the subspace, but furthermore, they are orthogonal. Can we do that? The answer is yes, and we have a process to obtain that called the Gram-Schmidt process. Once we have vectors that are orthogonal to one another, we can obtain an orthogonal basis. And once we have an orthogonal basis, we can describe vectors with respect to this basis through coordinate vectors. But more fascinatingly, we can take vectors that jut out of the space and calculate their projections using dot products. And projections are really useful because projections are fundamentally the idea of a best fit solution. Many equations just cannot be solved, but we can obtain approximate solutions to these equations. These are called the least squares solutions. And within the context of n-dimensional space, least squares solutions will always exist. In terms of some calculations, least square solutions will satisfy the same matrix equation pre-multiplied by the transpose. And a least square solution will always exist. There's even a nice formula that helps describe when this least square solution is unique. That is precisely when the matrix on the left is invertible. So we've looked at the ideas of the basis of a subspace, the eigenvectors of a transformation, and a basis being orthogonal. What if we had an orthogonal basis of eigenvectors? We have the best of all three worlds. In this case, we will say that the matrix A is orthogonally diagonalizable if it has eigenvectors that are orthogonal and forms a basis for Rn. But will we ever be this lucky? Can we ever get a matrix that is not only diagonalizable, but it is orthogonally diagonalizable? It turns out that there is a very simple criterion that says this is possible. This criterion is that the matrix A is symmetric. And there's a lot more to study in linear algebra from here on out. There are many ideas. We've just barely scratched the surface, and it's gonna be interesting. So let's take a zoom out, and this is the big picture of linear algebra. And yet, with this big picture in mind, you might still feel that, wait a minute, I need to do a bit more practice. I need to figure out how to apply these ideas into the problem-solving process. Perhaps this video on linear algebra will help you do just that.